All right. Hello, everyone. Welcome to lesson 26 of Calculus 1. Today, we're going to be talking about something called Newton's method, which is using derivatives in calculus to numerically approximate the solution to certain types of equations. So, for example, we could use Newton's method to help us approximate the solution of x squared minus 2 equals 0, for example. Now, you might say, well, I don't need to approximate the solution to this. I can get an exact answer if I add 2 to both sides, take a square root, and then we see that x can be either positive or negative square root of 2. Now, that's 100% accurate. You absolutely can do that. But what if you needed to know the decimal expansion for the square root of 2? Newton's method is particularly good at producing things like that. So Newton's method could give you that the square root of 2 is 1.4142, etc. So we're going to use Newton's method to get decimal expansions for things like the square root of 2 or other rational numbers. And we're also going to use Newton's method to approximate the solution to equations like e to the x minus x squared equals 0. Now, no matter how hard you try with algebra, you're not going to be able to get an exact answer for this. So this is a case where we absolutely need something like Newton's method because our algebra techniques won't give us an exact answer like we have here. So this is another opportunity to use Newton's method. However, Newton's method isn't perfect, and we'll see some examples where it will fail. So we'll also explore that as well. All right. So what is Newton's method? Let's introduce it here. So suppose we have a function f of x. And what we want to do is we want to find a root or an x value that makes f of x equals 0. So that's what a root is. A root is an x value where f of x will be 0. So that's our goal here. So if we use Newton's method in this case, f of x would be x squared minus 2. If we used it in this case, we'd have e to the x minus x squared. And you might be like, okay, well, what if I have an equation that I want to solve that doesn't have a 0 on both sides? Well, what you could do is you could subtract everything to the same side, and then that could be your equation. So for example, if we were presented with the equation e to the x equals x squared, we could use Newton's method on this by subtracting the x squared over to this side, or the e to the x over to the other side. Doesn't matter which. Okay, so that's what Newton's method's goal is to find a root. So how does it do that? Well, we need to do two things to use Newton's method. The first thing we do seems rather unscientific. We guess an answer, and we call this guess x sub 0. So this is our initial stab in the dark as to what our root could possibly be. And usually we base this maybe on a graph or some property of the function that we know about. We just have an initial guess. All right, and then the next thing we do is we follow tangent lines. So what we do is we follow tangent lines starting at where we have our initial guess, and this will lead us towards a more accurate example or a more accurate approximation. So here's graphically what's happening. Let's say that we have a parabola like this, similar to x squared minus 2. And let's say I guess that my initial root is going to be right here. So let's say that this is my initial guess. Maybe this is a nice round number like 1 or something easy to plug in. What I do is I go to that point on the graph. So I go to where we have x naught as our x value on the graph. I find the tangent line at that point, and I follow the tangent line to where it intersects with the x-axis. And whatever x value we get for that, that'll be called x1. So that's after the subscript here is the number of iterations we've done with Newton's method. So I go to this point x1, and notice that it's a bit closer to our true value or our true root right here. Then what I do is I repeat the same process. I go up to the curve where, with an x value of x1, I find the tangent line, and I go down to the x-axis. And that gives me x2, which at this point, it's already difficult to separate the true root with the approximation right here. So 2 iterations is already giving us a really good approximation of our root here. That's simply what we do. We get an x value, and then we follow the tangent lines to the x-axis. And if we repeat this multiple times, we'll get a more and more accurate approximation for the root to our equation. All right, now that's the graphical representation. So how will this work in practice? So what will we do mechanically to do this? Well, let's write down the equation of a tangent line, because that seems to be what we're working with here. The equation of a tangent line at a point x naught is y minus f of x naught is f prime of x naught times x minus x naught. So this is a tangent line at x sub 0. Now remember, our goal with the tangent lines is to get to the x-axis. And what defines the x-axis? It's where y is equal to 0. So what I'm going to do is I'm going to plug in y equals 0 here, and I'm going to solve for this x value right here, because that's what I want. I want the x value where the tangent line hits the x-axis. So I'm going to solve this equation now for x. All right, well, a 0 is a 0. We don't really need that anymore. I'm going to divide by f prime of x naught, assuming it's not 0. And we'll talk about what happens if it is 0 later. We have negative f of x naught over f prime of x naught is equal to x minus x naught. And then finally, to get my x, I'm simply going to add x naught over to this side, giving me that x naught minus f of x naught over f prime of x naught is my x value, which I'm henceforth going to call x1. So this is my new approximation for my root. And then I could either stop here, maybe one iteration of Newton's method is good enough, or if I want to repeat the process, I would simply replace all of these x naughts with x1. So I'm going to iterate this again. In fact, it wouldn't be too hard to write a computer program that repeats this process multiple times. So I plug x1 into here, do the algebra, and I would get this, except all of these would be x1s, and then this one would be something called x2. So in general, if I want to get to the next approximation, I would use the previous approximation, and then I would subtract the function value divided by the derivative value for this. So this is how I always get to the next approximation. The formula will be the same every single time. And remember, the idea of what we're doing here is we're following the tangent lines to the x-axis. All right, so that's how we perform Newton's method. So let's go ahead and take a look at the examples we presented in the beginning of class here. So let's say we want to approximate the square root of 2 to 3 decimal places. So we want to make sure that at least the first 3 decimal places are going to be correct for our square root of 2. All right, now how do we do this? Well, Newton's method is for solving equations of this form, where we have a function equal to 0. And what function should we use? Well, it seems like if we have x squared minus 2 equaling 0, we'll get x as one of the square roots here. I should put a plus or minus. And then we could just read off what decimals we get out of that and ignore the sign. So I'm going to have my function in this case be x squared minus 2. All right, now I want to use Newton's method to help me out here. So I'm going to figure out what this formula is going to be. So my xn plus 1 will be my xn minus, all right, well, I have the original function with xn plugged in. That'll be xn squared minus 2. And then I divide by the derivative of my function. And using the power rule, we see that the derivative is 2x. So I have 2xn here. Now, what we could do is we could clean this up a little bit. Sometimes we could do some simplification to help us. We have xn, and then this part right here will simplify to 1/2 xn. And then this part right here will be 1 over xn, when these twos cancel and the negatives cancel to give a positive here. And since these terms are similar, we can write this as 1/2 xn plus 1 over x sub n. All right, so we have that now. Now, we need to make an initial guess here. Now, I know that the square root of 1 is 1, so the square root of 2 needs to be something bigger than that. I guess I'll just start off at 1. I think that 1 will be relatively close. All right, so to get my x1, I'm going to plug 1 in for all of these x's, or rather into here. I have 1/2 times 1 plus 1 over 1, which will be 1/2 plus 1, giving us 3/2, or 1.5. All right, so this is our first approximation, but unfortunately not even the first decimal is right. We know that the square root of 2 is 1.4, so we definitely need to go further. All right, well, x2 can be gotten with 1/2 times 3/2, so now I'm plugging in 3/2 into this, and then I have 1 over 3/2. So this will be 3/4 plus 2/3, and that ends up giving us 17 over 12. We combine the fractions. Now, if we look at the decimal expansion for that, we have 1.416 repeating here. Okay, so I think these parts will be right, but we still need to get one more decimal point of accuracy. So I think one more Newton's method should do it. So I have 1/2 times 17 over 12 plus 1 over 17 over 12. And I'll save you the arithmetic here. When we end up simplifying this, this is going to be 577 over 408, which is equal to 1.414215, etc. All right, and then we go back up here to our first few decimals of the square root, and we see that not only do the first 3 match, but also the first 4 match as well. So we got a little bit more than we asked for here. So there we go. So this will be our decimal expansion for the square root of 2, at least accurate up to 3 or actually 4 decimal places. And notice that it only took 3 iterations of Newton's method to complete. All right, so that's our first example here. Remember, that's one use of Newton's method, is to get decimal approximations for numbers, irrational numbers like the square root of 2. We could also set up situations where we approximate pi or e or other numbers as well. All right, our next example will be addressing the other problem I posed in the beginning. I want to approximate a solution to the equation e to the x equals x squared. All right, so I want to find an approximate solution to this. And I guess 3 iterations work for this problem, so I guess I'll use 3 iterations of Newton's method for this problem as well. All right, well, I need to decide on a function I'm going to use. And remember, if we don't have something equaling 0, that's all right. We can subtract everything to one side. That will give us the function we need to use. Our function this time will be e to the x minus x squared because I want that to equal 0. All right, in order to use Newton's method, I need to know the derivative of this function, which will be e to the x minus 2x, using my derivative rules. All right, let's go ahead and set up our Newton's method formula. So we have x sub n plus 1 is x sub n minus, and then I have the function value, so e to the x sub n minus x sub n squared, and then that will be divided by f prime of x sub n, which will be e to the x sub n minus 2xn. All right, now unlike the other problem, I don't see any obvious simplification we can do here, so I think we're kind of stuck with this result right here. All right, now I need to make an initial guess. Now, unlike the other time where I at least had some idea of how big Newton's method was, for looking at this problem immediately, I don't really necessarily know where a root for this might happen. So if you're having trouble coming up with an initial guess, you can use things like the intermediate value theorem to help you. So e to the x minus x squared is a continuous function. So that means that if it's below 0 at one point and above 0 at another point, the root must be in between those two. So for example, if I look at f of -1, I have e to the -1 minus 1. That will certainly be less than 0. We don't even need to know. We just need to know that e is bigger than 1 for this to be true. All right, and then if I look at f of 0 on the other hand, I have e to the 0 minus 0, which is 1. That will be greater than 0. So that implies that somewhere in between these two values, I'm going to have a root. All right, now what I'm going to do is I'm going to use my x naught equaling 0 because that's going to be a relatively easy number to plug in. So hopefully I can hold on to some nice numbers for longer before I start getting into these bizarre exponentials. So x1 will be my x0, which is 0. So I have 0 minus e to the 0 minus 0 squared over e to the 0 minus 2 times 0. All right, lots of zeros here. The only non-zeros are these, which will be 1, and then we have a negative. So it seems like x1 will be -1. So I've simply gone to the other end of this interval. So our root is probably closer to -1 than it is to 0. All right, let's do a second iteration. Here we'll have -1 minus e to the -1 minus -1 squared. And then we have e to the -1 minus 2 times -1. And this will end up being approximately equal to -0.733. Now, this is assuming that I have a very accurate knowledge of what e is. So I used a calculator to give me e for this right here. Now, this answer here, this goes on forever because this is definitely going to be some irrational number here. So this is a non-repeating decimal expansion that goes on forever. Now, it would take a bunch of computing power to do that decimal expansion forever. So I'm going to just cut it off at 3 decimal places here. Now, that, while it might not seem that bad, can lead to something called rounding error if we do this repeatedly. So I could be off by, at most 0.001 here, or 0.0005 perhaps. But if I keep using these slightly incorrect numbers over and over again, eventually the error could compound to affect the higher decimal places as well. So this is something to be aware of if you ever cut off your decimals mid-calculation. So we are susceptible to rounding error at this point, but we're only going to be doing one more iteration, so it won't have that much time to propagate. All right, now we'll move on to x sub 3. So we have -0.733 minus e to the -0.733 minus that squared divided by e to the -0.733 minus 2 times -0.733. And once again, I used a calculator to perform this, assuming my calculator has a good idea of what e is. And we end up getting -0.703, which, by the way, agree with the first 3 decimal places that you would get if you used a computer to solve it. In fact, your computer is likely using a method very similar to this, solve your equation. So these are going to be the first 3 decimal places of my root here. So I was able to get that after only 3 iterations of Newton's method. So it's a relatively fast converging method in many cases. All right, so that's how we used Newton's method. Now I want to go over some possible pitfalls and weaknesses with Newton's method here. So it's not perfect. There are going to be instances where it's not going to work. So for example, let's say that I chose as my function e to the x. Now I want to use Newton's method on e to the x. Now you might immediately notice a problem here. Newton's method is good for solving equations like this, where e to the x, or whatever our function is equal to 0. But the problem here is that, as we know with exponential functions, they never equal 0. We have to send the limit to negative infinity for our exponential function to head to 0. So what happens if we use Newton's method on something that doesn't have a root? Well, let's find out. Let's see. So we have f prime of x will be e to the x because it's e to the x. So this means that x sub n plus 1 will be x sub n minus e to the xn over e to the xn. So it'll just be x to the n minus 1. What this is saying is our next guess for the root will be 1 less than our previous guess. So for example, if we guessed our initial root was 0, we would plug that into here, subtract 1, and x1 would be negative 1. We would do the same thing again to get x2. x2 would be negative 2. Now, this isn't converging to a particular number. This is just stepping backwards by 1, and it's going to do this forever. And because our root, you could say, is negative infinity, we're never really getting anywhere close to that. So this is an example of where Newton's method would fail when we don't actually have a root to find. Something similar would happen with other functions as well. If they don't have a root. So that's one obvious time to not use Newton's method, is if you know in advance that you're not going to have a root at all. All right, now let's take a look at another example. Let's say we want to approximate the square root of 5 using x squared minus 5 as our function for Newton's method. I know there's nothing wrong with this in principle. We did essentially the same thing to find the square root of 2 earlier in the video. But what if we chose as our initial guess x not equals 0? All right, well, let's see here. F of x is x squared minus 5. So f prime of x will be 2x. All right, so let's set up Newton's method here. We have xn plus 1 is xn minus x squared minus 5 over 2x. So these should be xn's. So when we simplify this, very similar to the way we simplified the earlier example, we have 1/2 x sub n plus 5 over 2 xn. Now, if we plug in x0 here, we would immediately run into a problem where we would be dividing by 0. So we can't use this value as an initial guess. And we would also need to stop using Newton's method if we ever obtain 0 as a guess for this particular method. Now, what was wrong with that? It was something that made the derivative be 0, because remember, we're always dividing by the derivative here. So if f prime of x naught equals 0, this is a bad guess. All right, now it's obvious algebraically why this is true, and geometrically it also makes sense, because if I draw the parabola for x squared minus 5, which will look something like this, x equals 0 will correspond to this point, where I have f prime being 0, or I have a flat tangent line. Now remember, the whole idea behind Newton's method is we were following tangent lines to the x-axis, but there's no way that we could follow a line that's parallel to the x-axis to the x-axis. There's no way we could set this equal to 0 and get something meaningful. All right, so there's that. So that's something that can happen. So we need to watch out where f prime is 0. And one final pitfall I'm going to mention. Let's say that we wanted to use Newton's method with x to the 1/3, and our initial guess will be x not equals 1. Now, this is something we realistically wouldn't use Newton's method on, because it's pretty obvious that the root to this would be 0, and we don't have any problems getting a decimal expansion for 0. So in all honesty, we probably wouldn't use Newton's method on this. But this illustrates something that can go wrong. If I find out what f prime is, I use the power rule, and I get 1/3 x to the negative 2/3. So let's see what happens if we set up Newton's method here. I have xn plus 1 is xn minus f of xn, so xn to the 1/3, divided by 1/3 xn to the negative 2/3. All right, now simplifying all this, 1 over 1/3 will be 3. And then 1/3 minus -2/3 will simply be 1. So this simplifies into 3xn. If we can combine with the initial xn to get -2xn. So our subsequent guess is based on our previous guess times -2. So if we start off with x naught being 1, this leads to x1 being -2, because I multiply 1 by the -2 here. Then x2 will be +4, so multiply this by -2. x3 will be -8. x4 will be +16. And I think you can see that this clearly isn't converging to 0. In fact, this is getting further away from 0 on every iteration here. So this is an instance where Newton's method will also not produce something meaningful. Now, one reason why this might be is that if we look at the graph of the cube root of x, it looks something like this. And notice that the root of our function is coincidental for where our derivative does not exist. So the tangent line here is going to be vertical. So if you ever have something where your derivative won't exist where the root is, you'll probably run into some issue like this. All right, that's all I have to say about Newton's method. So next class, we'll talk about our final application of derivatives before we move on to the next section of the course. I will see you guys then.